Hello everyone. Today we are going to discuss analysis of crystal. So in the previous lecture we have discussed different types of crystal systems based on different types of combinations of unit cells. Now those crystal systems is basically the regular repetitive arrangement of unit cells. So ultimately study of crystal depends on the study of unit cells. So once we define the parameters of unit cell, we can easily construct the crystal systems. So any analysis of crystals means analysis of the unit cell. Now these unit cells, if we build up in a regular repetitive way, we get the crystal system. So crystalline compounds or crystals have regular internal arrangement of grooves. Now this regularity in the arrangement internally, this study basically depends on the study of symmetry elements. So this regularity or the classification of different crystals into different crystals of a crystalline systems is basically based on the symmetry elements. Now these symmetry elements are nothing but the elements which are possessed by these crystalline systems. If we operate around these elements, the resulting structure is exactly identical to the initial structure. Those elements are known as symmetry elements. That means, take a particular substance, we operate either by rotation or by reflection. After this operation, the resulting structure, if appears to be exactly identical to that of original or initial structure, then the molecule or the system is possessed to have symmetry elements. So we have symmetry elements. Now we consider cubic system. So we have symmetry elements in cubic crystal. Symmetry element in cubic system. So I've defined you what is symmetry element. These are the elements. If on operation, the resulting structure is exactly identical to the original structure, those elements are known as symmetry elements. So in a cubic system, we have plane of symmetry, then we have axis of symmetry, then we have center of symmetry. So whereas these symmetry elements are present in perfect cubic crystals. Now we'll take up one by one. First take up plane of symmetry. Now, plane of symmetry is an imaginary plane which bisects the crystal or the cube into two equal halves such that the first half and the second half are exactly the mirror image of each other. So I repeat, it's an imaginary plane which bisects the cube into two equal halves such that the first half and the second half are exactly the mirror image of each other. These types of elements are known as plane of symmetry. So we have to assume a plane inside the cube so that this plane will bisect the cube into two equal halves such that both halves are mirror image reflection of each other. This is what we call as plane of symmetry. So under this plane of symmetry we have, so this is a plane which bisects the cube into two equal halves such that one half is a reflection of another half. Then this is what we call as plane of symmetry. Now in this plane of symmetry again we have two types of planes. Rectangular plane of symmetry and diagonal plane of symmetry. So we have rectangular plane of symmetry and diagonal plane of symmetry. So let's take a rectangular as well as diagonal plane. So we have a cube. Now in this cube we have to define the rectangular plane. Now take this plane. So we have a plane here. Now this plane bisecting two opposite face. This plane bisects the cube into two equal halves such that this half and this half is a mirror image. So we have a rectangular plane. In the same way, take this plane. This plane also bisects the cube into two equal halves such that the first half and the second half both are mirror image reflection of each other. And one more plane that we can take is take this plane. This plane also bisects the cube into two equal halves. So we have how many rectangular planes? So we have one plane, we have second plane, we have third plane. So in a perfect cube, there are three rectangular planes. So this is rectangular plane. Total number of rectangular planes in a cube is 3. Now let's take up an diagonal plane. Again, we have a cube. We have considered a cube. Now, in this cube, we have to consider diagonal plane. Now, let's take this. This is a plane along the body diagonal. So, if you take this plane along the body diagonal, so we say this is diagonal plane. Now, this plane bisects the cube into two equal halves such that this half and this half is a reflection. So, we have a plane here. Similarly, we can also consider this plane. So, we have a second plane. We can consider this and this plane. We can also consider this and this plane. Then we can consider this and this plane. Similarly, we have this plane and this plane. So total how many planes are there? 1, 2, 3, 4, 5 and 6. So in a perfect groove, there are 3 rectangular planes and there are 6 diagonal planes. So when we consider plane of symmetry in a perfect cube, we have a rectangular plane and we have diagonal plane. And the number of rectangular plane is 3 and number of diagonal plane in a perfect cube is 6. So total we have plane of symmetry. So total plane of symmetry in a perfect cube is 9. So out of these 9 we have 3 rectangular plane and 6 diagonal plane. So this is the plane, an imaginary plane which bisects the cube into 2 equal halves such that the first half and the second half are mirror image of each other. So this is rectangular plane and diagonal plane. The second one is axis of symmetry. Now, these axis of symmetry is an imaginary axis around which if the molecule or the cube is rotated by certain angle theta, the resulting structure and the initial structure both are indistinguishable, that is identical. So we have to imagine an axis passing through the cube, and around this axis this is to be rotated by a certain angle theta. After rotation of the cube by certain angle theta, the resulting structure and the initial structure both are exactly indistinguishable or identical. Those types of axes are known as axis of symmetry. Axis around which on rotation by angle theta gives a resultant structure which is identical to the original. So those type of axes are known as axis of symmetry. And these axes of symmetry are represented by Cn, where this n is the order of the rotation, and this n is equal to 360 by certain angle theta. So this theta cannot be 1, this theta cannot be 360, because if you rotate by 1 or if you rotate by 360, the result in structure is actually identical. So any form other than 360, we can have some order of rotation. So in this, we have C4 rotation. So therefore, for this C4, theta is equals to 90 degree. Then we have C2, theta equals to 190 degree, and C3, where theta equals to 120 degree rotation. That means we have to define this C4 axis. That means angle 90 degree rotation. So by this 90 degree rotation, we are getting actually identical structure. And C2 180 degree rotation, and C3 120 degree rotation. Now let's define how many C4, C2 and C3 axes are present in a cubic crystal. Let's consider again a cube. So we have a cube. Now in this cube, you have to define C4 axis, C2 axis and C3 axis. So in C4 axis, we have angle 90 degree rotation. Now let's assume an axis passing through the centers of the opposite phase. So this is the opposite phase. Now we assume an axis passing through the centers of opposite phase. Now we rotate around this axis by an angle 90 degree. So we have an axis passing through the centers of opposite phase, and we rotate around this axis by angle 90 degree. Now this gives you an identical structure which is exactly same as that of the initial structure. Means the structure obtained after rotation and structure before rotation, both are exactly identical. So in a cube, we have 6 phase. So two opposite phase, we have an axis passing through the centers of two opposite phase. So we have how many C4 axis? 1, 2 and 3. So total C3 axis in a cube is 3. So we have number of C4 axis 3. One axis, two axis, front and the rear face. Second, we have C2 axis, the rotation by 180 degree. Now for this C2 axis, we have to assume an axis passing through the centers of diagonally opposite edges. Take this edge and take this edge. Diagonally opposite edge centers. We assume an axis passing through this centers of edge of two diagonally opposite edges. So we rotate around this axis by an angle 180 degree. These after rotation gives a resulting structure which is exactly indistinguishable from the initial structure. So we have an axis which is what they call as C2 axis. So therefore look at this. So we can have these axis, we can also have these axis, we can also have this axis, we can also have this axis, we can also have this and this one axis, this one and this one axis. So how many C2 axes are present in a given cube? So 1, 2, 3, 4, 5, 6. Total C2 axis in a perfect cube is 6. So this is passing through the centers of diagonal opposite edges. The next one is C3, that is rotation by angle 120 degree. Now for this VS axis passing through this diagonal. So we have this body diagonal, we assume an axis passing through the body diagonal. We rotate around this, then it gives you C3. So in a cube, there are 4 body diagonals. So total number of C3 axes possible in a perfect cube is 4. So therefore we have to look at this. Total number of C4 axes is 3. Total number of C2 axes possible in a perfect cube is 6. Total number of C3 axes possible in a perfect cube is 4. So total number of axes of symmetry possible in a perfect cube is 13. So there are 13 axes of symmetry. Out of which we have 3C4, 4C3 and 6C2 axis. Total giving you 13 axes of symmetry. And after this we have center of symmetry. So the last one is center of symmetry. In any cube we have only one center. If a particular line is drawn on the opposite direction, we get exactly identical face or exactly identical point. So every cube has a center of axis. So total number of center of axis possible in a perfect cube is 1. So we have one center of axis. We have how many axes of symmetry? 13. And how many plane of symmetry? 9. So total number of symmetry elements present in cubic crystal is 23. So there are 23 symmetry elements in a perfect cube, out of which we have 9 plane of symmetry. Out of these 9 plane of symmetry, we have 3 rectangular and 6 diagonal. Total number of axes of symmetry is 13. Out of these 13, we have 3C4, 6C2 and 4C3 axes. Then we have only one center of symmetry. So total number of symmetry elements present in a perfect cube is 23. This is what we call symmetry elements. So based on these symmetry elements, we have classified the crystals into 7 crystal systems. So basically, classification is based on these symmetry elements. So having gone through these symmetry elements and the types of crystals and every crystal, how many possible arrangement of lattice point. Based on this, we have discussed Bravais lattice. So there are 14 Bravais lattice. So these crystalline substance crystals are possessing these forms. In all these crystals, we have to study the unit cell. So let's come back to analysis of crystals, that is analysis of unit cell. Analysis of crystals. This is nothing but unit cell. So the properties of crystal is nothing but the properties of its unit cell. So once we identify the unit cell, we can easily identify the properties of the crystal. So analysis of crystals. Under this heading, we are going to discuss arrangement of spheres or atoms. Then we will define rank, effective number of atoms per unit cell. Then we define distance of closest approach. This distance of closest approach is the closest distance between two adjacent spheres or atoms in a crystal system. So this is what we call as distance of closest approach or closest distance between any two adjacent atoms. Then we'll define the radius of sphere or radius of atom, because each lattice point is occupied by atoms, molecules or ions, and we assume this to be spherical in shape. Then we will have the radius of sphere or atom, coordination number Cn. Now this coordination number is defined as the number of atoms or spheres surrounding a particular atom or sphere at the closest distance, as a nearest neighboring distance. So take any particular point or a sphere. So how many spheres are surrounding this particular sphere at the closest distance? So this is nothing but the nearest neighbors. So these nearest neighbors is what we call as coordination number. So different unit cell will have different coordination number. Then we have density of unit cell. Now the density of unit cell will be actually identical to the density of crystal. So to define the density of crystal, we have to define the density of a unit cell. Then we have packing fraction or packing efficiency. Then we have void fraction. Then we have the unit cell dimension. So while discussing the unit cell, we have to identify this. That is how different atoms or spheres are arranged in a unit cell. What is the effective number of atoms present per unit cell? What is the distance between the closest distance between any two adjacent spheres? What is the radius of atom or sphere? What is the coordination number? What is the nearest neighbors of any particular atom or sphere? What is the density of crystal? What is packing fraction? What is void fraction? And what is the unit cell dimension? Now there are some terms like density, packing fraction, void fraction. So let's define what is density. Now going by definition of density, density is defined as mass per unit volume. Since we are defining density of unit cell, this density is mass of unit cell divided by volume of unit cell. So we define this density as mass of unit cell divided by volume of unit cell. So we are assuming this unit cell to be cubic. So if we have a cube with S length A, then the unit volume of unit cell will be S length cube. So these mass of unit cell, because in unit cell we have the sphere, so this mass is nothing but the effective mass of the spheres present in the unit cell. So this is mass of effective spheres of the unit cell divided by volume of unit cell, that is A cube, if A is the S length of the unit cell. Mass of effective sphere or mass of effective atoms, because we consider these atoms to be spherical in nature, so we define these atoms or sphere or spheres as atoms. So mass of effective spheres is equal to ring into mass of single atom divided by A cube. So effective atoms means effective number of atoms present per unit cell. So that is defined as ring. So ring into mass of single atom, that is mass of effective atoms present in the unit cell. So we have this J into, let the mass of single atom be m, small m, divided by A cube. Now rather than defining in terms of mass of single atom, we define in terms of gram molecular mass. Now we define this gram molecular mass as mass of single atom multiplied by Avogadro number. So mass, molecular mass or gram molecular mass is the mass of 1 gram molecule, that is Avogadro number. So mass of single atom multiplied by Avogadro number, this gives you gram molecular mass. So therefore mass of single atom is molecular mass divided by Avogadro number. So we replace this mass of single atom by molecular mass. So therefore this comes out to be Z into molecular mass divided by Avogadro number into A cube. So this density is Z, that is ring, effective number of atoms per unit cell, multiplied by gram molecular mass divided by Avogadro number into A cube, where A is the S length of unit cell. So this is how we define density of crystals. So every unit cell will have different values of Z and different values of A. So this is density of unit cell. Now coming to packing fraction. Let's see what is the meaning of packing fraction. Packing efficiency or fraction, PF. Now this packing efficiency or fraction is the fraction of the total volume of cube occupied by spheres or atoms. So we have a cube. In this cube we have lattice point being occupied by atoms or spheres. So these atoms or spheres occupying lattice point will occupy certain volume. So out of this total volume of cube, how much of the volume is occupied by atoms or sphere, that is what we call as packing efficiency. So therefore this packing efficiency is defined as volume occupied by spheres divided by volume of unit cell. So this ratio is defined as packing fraction. Multiply this fraction, this will give you percentage of packing efficiency. Volume occupied by spheres, this is equals to length into volume of single sphere. So this defines effectively volume occupied effective spheres. So effective sphere means effective number of atoms per unit cell multiplied by volume of single sphere. This is the total volume occupied by sphere divided by volume of unit cell, that is A cube. Now volume of single sphere. So we have J into 4 by 3 pi r cube. Volume of sphere is 4 by 3 pi r cube divided by A cube. So where this r is the radius of sphere. So this is how we define packing efficiency. So simple definition is fraction of the total volume of unit cell occupied by spheres. So this is volume occupied by the spheres divided by volume of unit cell. So this is, so depending on the unit cell, we'll have different values of Z and the relation between A and R. Once we define, we can easily define what is the packing fraction. Once we define this packing fraction, so we have a volume. Out of this volume, certain volume is occupied by spheres. Then the remaining space, unoccupied space, that is defined as void fraction. So this void fraction is the fraction of volume left unoccupied. Fraction of volume in a unit cell left unoccupied by space. That is what we call as void fraction. So this void fraction is equal to 1 minus packing fraction. If this is the total volume occupied, so 1 minus total fraction of the volume occupied, that gives you void fraction. So this is how we define packing efficiency, void fraction, density. Then now we'll define all these parameters individually for different unit cells like simple cubic cell, face center cubic cell, body center cubic cell, hexagonal hexagonal unit cell. So first take out simple or primitive unit cell. Simple or primitive cubic unit cell. Simple cubic simple or primitive cubic unit cell. So first one is arrangement of spheres. How these spheres will be arranged in a simple or primitive unit cell. In a given unit cell, if the lattice point or the spheres occupies only the corners of cube, then that is the simplest arrangement of atoms or spheres in a unit cell. That is what we call as simple or primitive unit cell. So coming to arrangement, so we have this. a unit cell. Now, if the lattice point is only at the corners of cube, so in a simple or primitive unit cell, how the spheres are arranged? Occupies only the corners of cube. Now, so this is the arrangement of spheres in a simple or primitive unit cell. So these atoms or spheres occupy only the corners of cube. This is the simplest arrangement that is possible for unit cell. So, but the condition for this arrangement of spaces, any two adjacent corner atom, any two adjacent corner. This is adjacent corner, adjacent corner, adjacent corner. Any two adjacent corner spheres should be in contact with each other. Any two adjacent corner, any two adjacent corner spheres should be in contact with each other. So this is the condition for arrangement of spheres in a simple or primitive. Spheres occupying only the corners of cube, and these two adjacent corner spheres should be in contact with each other. So this is the arrangement of spheres. Now after this, we define second parameter. So I have given you what is the arrangement of spheres and what is the condition required for arrangement of this sphere. Now let's suppose the A's length, this distance, this is the A's length, this distance be A. A's length A. So this is A, this is also A, this is also A. Now distance of closest approach. Or the closest distance between two spheres, that is known as distance of closest approach. Now, while mentioning the arrangement of a sphere, I have given a particular condition that any two adjacent corner atoms should be in contact with each other. So the closest distance means take this sphere, these two spheres should be in contact with each other. If these two adjacent corner spheres are touching with each other, then what is the closest distance between these two spheres? That is equals to S length A. So therefore, closest distance, that is with D, so the closest distance is equal to S length of the unit cell. So this D is equals to A, if A is the S length of unit cell. So the closest distance between any two spheres in simple or primitive unit cell is equals to the S length A. If this is the closest distance, then next is the radius of sphere. The radius of sphere, that is R. Now these two spheres are in contact with each other. So half of the contribution coming from this sphere, another half will be coming from this sphere. If R is the radius of this sphere, then this distance is equals to twice R. half radius is coming from this, another radius is coming from this, and these two are in contact with each other. Therefore, the edge length A is equals to R. So therefore, R is equals to half of edge length, or we can say this is the closest half of the closest distance. So half of the closest distance is equals to the radius of sphere in case of primitive unit cell. Number 4, we have defined arrangement, closest distance, radius of sphere. Then this Z or ring, effective number of spheres per unit cell. In this unit cell, spheres occupying only the corners of cube. If the spheres occupying only the corners of cube, then the contribution of each corner is 1/8. That means each corner is equally shared by 8 unit cells. So the contribution of these corner is 1/8. So number of corner atom is 8. Contribution of each corner atom is 1/8. So effectively, only one sphere is present per unit cell, though we require 8 spheres to construct a simple or primitive unit cell, but effectively only one sphere is present per unit cell. That is what we call as J ring. Number 5, we have to define density. This density is equals to J into molecular mass divided by Avogadro number into A cube, where A is the S length, Z is the effective number of atoms per unit cell. So J for this simple or primitive unit cell is 1. So this is M divided by Na into A cube. So A can be defined in terms of R. So A is equals to twice R. So we can replace, if the radius of atom is given, then also we can define A. So this is the density. Number 6, we have packing fraction. So we define this packing fraction as volume occupied by spheres divided by volume of unit cell. So volume occupied by sphere is J into volume of single sphere, that is 4/3 pi r cube, divided by volume of unit cell. So Z is 1, so we have 4/3 pi r cube divided by A cube. So for a simple or primitive unit cell, A is equals to twice R. So this comes out to be twice R cube. Or if you look at this, that is 4/3 pi r cube divided by 8 r cube. So this comes out to be pi by 6. So pi by 6, this is approximately 0.52. That means only 52% of the total volume is occupied by spheres. If only approximately 50% is occupied, so the remaining 50% is unoccupied. So therefore, void fraction. So void fraction is 1 minus taking fraction. So this is 1 minus 0.52, that is 0.48, or approximately 48% of the volume is unoccupied by the spheres. That is the void fraction. Then we have the unit cell dimension. So we have this density. So we have density is equals to m by n a cube. So therefore, unit cell dimension is this a as length. So as length a is equals to m by density into Avogadro number cube. So once we define this density of a unit cell, from this density we can measure the as length A. So as length A is equals to molar mass divided by density into Avogadro number and cube root. This gives you the unit cell dimension. So we have defined arrangement, distance of closest approach, the radius of sphere, ring, density, taking fraction, void fraction, and unit cell dimension. Now, what is left is coordination number. Coordination number, as we have defined earlier, this is the how many neighbors are present at the closest distance. At the closest distance, a particular atom is being surrounded by how many atoms? That is what we call as coordination number. So, the closest distance, as we have defined earlier, distance of closest approach, this is as length A. So, for a primitive unit cell, the closest distance is as length A. So, at this as length A, how many spheres are being surrounded by around a particular sphere? So, we consider a unit cell. We have a unit cell. Now let's consider this. So we have point here, we have point here, we have point here. Considering this to be the reference center. So how many atoms are present at the closest distance? This is the closest distance, this is A, this is also A, this is also A. So we have now above this unit cell, we also have a unit cell. So above this unit cell, at this distance A, again we have one sphere. At the side of this unit cell, again we have one unit cell. Again at this distance, we'll have another atom. So we have this unit cell. So in a simple or primitive unit cell, so the coordination number of this atom at the closest distance. So we have 1, 2, 3, 4, 5, 6. So we have look at this. This is distance A, distance A, distance A. Now above this, we also have a unit cell. So we will have one atom. In the front side, we also have a unit cell. So we have one atom. On the other side, right hand side, we also have a unit cell. So the total number of atoms surrounding a particular atom in a closest distance, that is coordination number, this comes out to be 6. So in a simple or primitive unit cell, coordination number is 6. Now coming to second, that is body center cubic. Unit cell, simply known as BCC. So we have body center cubic. So first, let's discuss arrangement of space. So we consider a cube. The lattice point occupies the corners of cubes, similar to that of primitive unison. Along with these spheres occupying the corners of cube, one more sphere is present exactly at the center of cube. So this is the arrangement. So arrangement is corners of cube and body center. So we have spheres occupying corners as well as the center of cube. Subject to the condition, so condition being any two adjacent corners atoms will not be in contact with each other, but the body center sphere will be in contact with 8 cornered spheres. This is the condition for arrangement of lattice point. Any two adjacent corners will not be in contact with each other, but this body center atom will be in contact with 8 corner atoms. That means we have to show in this way. Again, we consider so these body center atom will be in contact with these corner atoms. The length is distance that is distance in body diagonal, and if this is the center of two. This is R, this is R, this is R, this is also R. E, B, C, D. Now we have to define the body diagonal. This is distance A, this is also distance A. Now let's define closest approach. Closest distance. Now we have a right angle triangle ABC. So using Pythagoras theorem, we have AB square is equals to AC square plus BC square. So this is A square plus A square or YC square. Now again we have another right angle triangle, that is ABD. So in this ABD we have AD square will be equals to AB square plus BD square. AD square is YC square, BD square is A square, so this is 3A square. Therefore, the body diagonal AD is equals to A root 3, that is body diagonal. So these body diagonal total distance is 4 times r, 1, 2, 3, 4. So this is a very important relationship for body center cubic. So the body diagonal is a root 3, which is equals to 4 times r. So this is now we have to consider the closest distance. These two spheres are in contact. So this distance is what we call as the closest distance. So therefore the closest distance between any two adjacent spheres in a body center cubic is half of body diagonal. So this is a root 3 by 2. So this is half of body diagonal. A root 3 by 2. If this is the closest distance, then let's define what is the radius of sphere. The radius r is half of closest distance, that is a root 3 by 4, which is equals to 1/4 into body diagonal, yes. 1/4 of body diagonal or half of the closest distance is equals to radius of sphere in case of body center cubic. Number 4, let's define Z, effective number of atoms per unit cell. We have 8 corner atoms, contribution is 1 8 plus we have 1 body center atom. So effectively there are 2 atoms per unit cell. Number 5, look at this coordination number. The closest distance, this is the closest distance. At this closest distance, this body center atom is in contact with 8 corner atom that we have defined there. The body center atom will be in contact with 8 corner atom. So therefore the coordination number is 8 in case of BCC. Number 6, density is Z into molecular mass divided by Avogadro number into A cube. So in case of body center cubic, Z is 2. So we have 2n divided by Na cube. If this is the density, then unit cell dimension A as length is equals to 2m by density into Avogadro number cube root. So we have unit cell dimension, we have density, coordination number, effective number of atoms, radius, closest distance, arrangement. Then we have taking fraction. Taking fraction is volume occupied by sphere divided by volume of unit cell. So effectively how many volumes? Sphere 2. So 2 into volume of single sphere, that is 4 by 3 pi r cube divided by a cube. Now either we can replace r in terms of a or a in terms of r. So r is a root 3 by 4. Or we have this relationship a root 3 is equals to 4r. We can define r in terms of a or a in terms of r. So we have r is a root 3 by 4. So we have 2 into 4 by 3 pi r cube a root 3 by 4 cube divided by a cube. So let's simplify this. So we have a pi a cube into 3 root 3 divided by 3 into 4 cube What means 64 into a cube. 4 is 16, 16 into 4, 64. So we have a cube cancel, t cancel. So this comes out to be pi root 3 by 12. 5, if you solve this comes out to be 0.68. That means 68% of the volume is occupied by spheres. So if this is the taking fraction, then the whole fraction is 1 minus taking fraction. So this is 1 minus 0.68. So comes out to be approximately 32. So approximately 32% is left unoccupied by spheres. So this is the unit cell parameters of a body center cubic unit cell. Now once we have this body center cubic unit cell, we'll define face center cubic unit cell. Face center cubic unit cell, that is FCC. So first we'll take out arrangement of spheres. Arrangement of spheres in a face center cubic unit cell. So we have a face center unit cell. In this face center unit cell, spheres occupying as usual corners of cube. All 8 corners will be occupied by spheres. Along with these, the centers of each face will also be occupied by spheres. We have this front face, we have this rear face. So, considering this arrangement, corners and the centers of all 6 faces will be occupied by the spheres. Right face, left face, top, bottom, front, and the rear face, along with these corners. But subject to the condition is any 2 adjacent corners should not be in contact with each other. Any 2 adjacent corner spheres will not be in contact with each other, but the face center sphere will be in contact with 4 corner spheres in the same face. That means this face center atom will be in contact with these 4 corner atoms in the same face, and the face center atom will also be in contact with those face center atoms or spheres having common edge. So that means these two corner atoms will not be in contact with each other, but these face center will be in contact with four corner atoms in the same face. Along with this, these face center will also be in contact with these face center having this common edge. These face centers will be in contact with these face center having common edge. This face center will also be in contact with this face center having this common edge. Similarly, these face center will be in contact with this face center atom of the rear face having common edge. So this is the condition for arrangement of face center cubic unit cell. If this is the condition, then we'll have defined closest distance. We'll define the closest distance in an FCC. The corner atoms will be in contact with the face center atom. So let's take this. Let's take this face. Here this face center atom. So we have this atom, this is the face center atom. This distance that is face diagonal. Total distance, this is R, this is R, this is also R, this is also R. Now let's take this. This is A, B, C. So in right angle triangle ABC, triangle ABC, AC square is equals to AB square plus BC square. So this is twice A square. So therefore, face diagonal AC is equals to A root 2 face diagonal. So therefore, closest distance is half of face diagonal this distance. So that is A root 2 by 2. So this phase diagonal is equals to 4 times r. This is the relation in case of phase center cubic. If this is the case, then the radius r is equals to half of closest distance. The closest distance is a2, so this is a root 2 by 4, or we can say this is 1/4 of phase diagonal. So this is the radius of sphere in case of FCC lattice. Then we have Z, effective number of atoms per unit cell. We have 8 corner atoms, contribution is 1/8. Plus we also have atoms occupying centers of phase. There are 6 phases, so there are 6 spheres at the centers of phase. Each phase is equally shared by 2 other atoms, unit cells, so contribution is half. So this comes out to be 1 plus 3, that is 4. So effectively there are 4 spheres per unit cell in case of FCC lattice. Next we have look at this density. Density is Z m by Avogadro number into a cube. So Z is 4. So 4 times m divided by na cube. If this is density, then unit cell dimension A is equals to 4m divided by d into Avogadro number cube root. Coordination number. Now look at this coordination number. Condition clearly says any 2 adjacent corner atoms should not be in contact with each other, but a phase center atom will be in contact with 4 corner atoms in the same phase. Plus, each phase center atom will be in contact with those phase center atoms having common edge. So if you look at this, take this phase center. Now for this phase center atom, the atoms or spheres that will be touching with this phase center atoms will be these corner atoms in the same phase. Condition also says the phase center atoms will also be in contact with those phase center atoms having common edge. So with this phase is having common edge, so this will be in contact with this phase. This left phase also having common edge. This phase and the front phase having common edge. This phase and the rear phase, this is also having common phase. So therefore, the coordination number of this will be 4 in the same plane, 4 below, that is unit cell above this also, above this unit cell again will have 4. So total number of spheres in contact with these phase center atoms will be 12. So the coordination number of spheres in phase center cubic. So out of these 12 we have 4 in the same plane, 4 below the plane, and 4 above the plane. So total coordination number is 12. Then we are left with taking fraction. Taking fraction. This is volume occupied by space divided by volume of unit cell. So that is J into 4 by 3 pi r cube divided by a cube. There is 4 into 4 by 3 pi r cube divided by a cube. So for a FCC, this is the relation between r and a cube. So therefore 4 into 4 by 3 pi r cube is a root 2 by 4 cube divided by a cube. So we say this is 4 into 4 into a cube into 2 root 2 into 5 divided by 3 a cube into 4 cube. So a cube will cancel out, 4 square will cancel out, 2 will cancel out, so we are left is 5 root 2 by 6, and if you replace 5 by 22 by 7, you get is 0.74. That is 74% of the cube is occupied by sphere. If this is the packing fraction, then the void fraction is 1 minus packing fraction, so 1 minus 0.74, so that is 0.26. So approximately 26% of the unit cell is left unoccupied by spheres. So this is the unit cell parameters of simple, primitive, body center and FCC type. So combining all this, let's give in a tabular form. So we have simple cubic unit cell. We have body center cubic unit cell. We have face center cubic unit cell. So we have first closest distance is S length A. Closest distance is half of body diagonal, that is A root 3 by 2. This is half of face diagonal, so this equals to A root 2 by 2. Radius, so this is E equals to twice R, so therefore R is equals to half of the closest distance. In case of BCC, we have 4R is equals to A root 3, therefore R is equals to A root 3 by 4. FCC, 4R is equals to A root 2, so therefore R is equals to A root 2 by 4. Effective number of atoms per unit cell, 1. Effective number of atoms per unit cell, 2. Effective number of atoms per unit cell, 4. Coordination number, this is 6. BCC, 8. FCC, 12. Density D, that is n by Avogadro number A cube. BCC, 2 into molecular mass divided by Avogadro number A cube. FCC, 4 into molecular mass divided by Avogadro number A cube. S length A, n by Avogadro number density cube. BCC twice n by Avogadro number density cube root. FCC 4m by Avogadro number density cube root. Then we have packing fraction 5 by 6, which is equal to 0.52 or 52%. BCC pi root 3 by 8. This is equals to 0.68 or 68%. FCC pi root 2 by 6. This is equals to 0.74 or 74%. Void fraction 1 minus pi by 6. This is equals to 0.48 or 48%. BCC 1 minus PF, which is equals to 1 minus pi root 3 by 8. This comes out to be 0.32 or 32%. FCC 1 minus PF, which is equals to 1 minus pi root 2 by 6. So this comes out to be 0.26 or 26%. So these are the parameters for simple unit cell, body center unit cell, FCC unit cell, chest center. And if you look at this, packing fraction is least or minimum in case of simple or primitive, that is 52%, then maximum in case of FCC. So when we consider the packing efficiency or the packing fraction increases from simple to body center to FCC tag. This is the parameters for these three types of unit cell. Now after this, we'll take up hexagonal unit cell. So let's go for this hexagonal unit cell. Hexagonal closed packing. This is HCP. Hexagonal closed packing. Now let's define this hexagonal closed packing, how atoms are arranged, what is the coordination number, what is the effective number of atoms, and packing efficiency. It is something like regular hexagon. Filter the centers. Let this distance, this is height, and this distance, this is half of the height. So while arranging the atoms, the corners is occupied by spheres and the face of this regular hexagon is also occupied by spheres. Along with this, at the center there are three spheres forming equilateral triangle. This is the relative arrangement of. So while discussing this, look at this. Atoms are occupying corners of regular hexagon, as well as centers of this regular hexagonal face, and there are three atoms exactly at the both center of forming equilateral triangle. These face center is in contact with six corner atoms as well as three above. So arrangement says spheres occupying corners of hexagon and centers of hexagonal face, and three spheres at the center forming equilateral triangle, subject to the condition being face center atom is in contact with six corner atoms or spheres as well as three central atoms which is placed above or below. If this layer be A, this layer is B layer, then this layer is again A. Exactly A and SM, in between this we have this B layer. So basically this hexagonal close bracket consists of A, B, A, B, A, B type. So if this is the condition, so we have this. Let this with the distance A, then closest distance between any two is S length A. If R is the radius of a sphere, then radius R is equal to A by 2, half of this S length. Now considering effective number of atoms per unit cell, so we have spheres occupying corners of hexagonal face. So there are how many corners? 12 corners. And now let's see the conservation of each corner. Now this corner is in contact with how many unit cell? So let's take this. So we have one unit cell, we can have another unit cell here, we can also have another unit cell. That means each corner atom having a contribution of how much? 6 unit cell. 3 in the plane, 3 below the plane. If you look at this, we can have 1 unit cell here. We can also have 1 unit cell here. So this point is in contact with 1, 2, 3 in the plane. Below this, we will also have 3. Then we have phase center. Each phase center is equally shared by 2 unit cells. So contribution is half. And we have this 3 body center. So each body center is equally shared by only 1 unit cell, that is 3. So we have 3 plus phase center, we have 2, contribution is half, plus we have 12 corner, and each corner is equally shared by 6 unit cell, 3 in the plane, 3 below the plane. So total number of atoms per unit cell is 3 plus 1, 4 plus 2, 6. So effectively there are 6 spheres per unit cell in any hexagonal closed packing. While considering this, coordination number of hexagonal closed packing is, let's see, this sphere is in contact with 6 corner atoms plus 3 above the plane plus 3 below the plane. So this atom is in contact with 12 atoms at the closest distance. So the coordination number is 12. Now this coordination number is exactly identical to that of FCC type. If the coordination number is same, then packing fraction will also be same. So in case of hexagonal closed packing, packing fraction is again 74%. If this is the packing fraction, then void fraction, that is 0.26 or 26%. And in this locations we have defined, we have A layer, above this we have B layer, above this we have A layer. So arrangement is A, B, A, B, A, B. A, B, A, B, A. So these hexagonal closed packing having same coordination number with that of FCC. These FCC and hexagonal closed packing, these are known as closest pack structure. So after this we'll have closest pack structures. Now these closed pack structure, we have FCC, phase center cubics, or known as cubic closed packing, and we have hexagonal closed packing. These two structures, hexagonal closed packing and FCC or cubic closed packing, these are known as closed packed structure. Why they are known as closed packed structure? Because of the maximum packing fraction. So packing fraction is 0.74. Since the packing fraction is maximum in case of this hexagonal and FCC, these are known as closest packed structures. Now these two different arrangement of lattice point having same closed pack. Why they are having same packing fraction? Because of the same coordination number. So the same packing fraction of FCC and HCP that is 0.74 is due to having same coordination number. So if question says why two different lattice structures, hexagonal cross packing and cubic cross packing, have same packing fraction? Because of same coordination number. Why these are known as closed pack structure? Because of the highest value of packing fraction. Now in this FCC, the arrangement of layers is ABC type. Whereas in case of FCP, as I have mentioned earlier, that is AB type. So these two structures having same coordination number, same packing fraction is classified as closed packed structures. So these are different dimensions regarding different types of unit cell.